All right, Module 13, we're getting to the end of it. In your second edition of the Apologia Chemistry textbook, we are covering pages 439 to 442. And someone also pointed out to me that if you have the third edition, my modules numbers are a little different. So if you have the third edition of the Apologia Chemistry textbook, this would be Module 12. It's the module that talks about enthalpy, and today, entropy. So what's entropy? Entropy is a measure of the disorder that exists in any system. It is written with a capital S, don't ask me why, and its units are joules per mole times Kelvin, or kilojoules per mole times Kelvin, or kilocalories per mole times Kelvin. Okay, so entropy is the measure of disorder. Now that we have a definition for entropy, we can talk about the second law of thermodynamics. But first, do you remember what the first law of thermodynamics is? That's right. It is that energy can be neither created nor destroyed. Energy in the universe must stay at the same. It can change from potential to kinetic energy, but the amount of energy stays the same. Okay, now for the second law of thermodynamics, talking about entropy, the entropy of the universe must always increase or stay the same. So the disorder in our universe either stays the same or increases. It can never decrease. And hopefully you have read in your book about entropy already, and so you know that the example the book gives is of a vase sitting on a mantle. There's low entropy there because the molecules of the vase are packed closely together in a very orderly way, creating a beautiful vase. But if the vase falls and shatters into hundreds of tiny pieces, the entropy has increased. There is much more disorder in the room because there's all these little pieces of vase all over. It's the same with the universe. Or for example, my yard. As I look out into my spring yard, I can see that the disorder over the winter has increased because the leaves have blown around, there are more sticks on the grass. I need to get out there and do something about it because the disorder just keeps increasing. Okay, entropy of a substance changes with phase changes. Okay, so now we're going to talk about how the entropy of a substance is affected or how it can change. One way it can change is with phase changes. For example, in a solid, we have low entropy, or capital S. Because, as we talked about with the vase, the molecules are held closely together in a solid. They can't move very much. They can vibrate a little bit, but there they are. Hi, I'm a molecule. I'm just vibrating a little bit. I'm not showing a lot of disorder, just a little bit of disorder. Okay, so did you like my impersonation of a molecule? A solid has low entropy, low disorder. Now compare it with a liquid. Here comes my impersonation of a molecule again. This time I'm a molecule in a liquid, and I have a little bit more room so I can move around a little bit more. I'm showing a little bit more disorder. I'm a little harder to control. Of course, I'm still bound within the edges of my container, but I'm showing more disorder. So in a liquid, we have higher entropy, or S. Then comes a gas. A gas, those molecules can move wherever they run, right? They are running all around the room. They are very hard to control and showing a lot of disorder. So a gas shows the most disorder, highest entropy. Okay, so entropy changes with phase changes. Another way that entropy can change is with temperature. Entropy of a substance changes with temperature. And as you might be able to guess, with increasing temperature comes increasing disorder or increasing entropy. Thank you. Because those molecules, as we have learned in the kinetic theory of matter, as you increase the temperature of molecules, they start moving around faster, right? And so those molecules, you can also relate it to phase changes, because molecules in a solid, as they start moving around more, they need more room and they escape and become a liquid. So with temperature, as it increases, the molecules move faster, they're harder to control, which leads to more disorder or higher entropy. Entropy also changes with the amount of matter. Okay? Consider the room I'm in right now. There's only one person in this room, blessedly, and so the disorder is relatively low. And I have warned all of my children, I'm making a chemistry video, leave me alone. But if one of them, or two of them, or three of them, or four of them were to enter into this room, the disorder would increase. So as we increase people, or molecules, or atoms, or matter, we increase the disorder, we increase the entropy. So let's write that. Entropy, okay, increasing matter leads to increasing disorder. And I'll give you an example of this one too, so we don't only talk about people and homes and yards. We'll talk about an actual gas now. For example, 5 moles of gas has higher entropy than 3 moles of gas. And I will also give you an inequality showing the second law of thermodynamics. We can also write it as delta S of the universe, and hopefully you recognize that delta means the change. So the change in entropy of the universe must either stay the same or be greater than 0. Okay? And let me write that out as a little sentence here for you. The change in entropy of the universe stays the same, which would be, then the change would be 0, right? Or the change in entropy of the universe is greater than 0, which would mean it increases. Oh no. Speaking of increasing entropy, I just heard someone from downstairs yell, "Mommy." So I shall be right back. Okay, I'm back, and I need to add an addendum to the second law of thermodynamics. If you want to decrease the entropy in a system, just turn on Dora. Okay, seriously, let's learn about something else. To determine the sign, if it's positive or negative, for delta S in a chemical reaction. Okay, so in a chemical reaction, does the delta S, the change in entropy, is it positive or is it negative? Here are some rules to follow. The side of the reaction with more gas molecules or more gas atoms has the highest entropy. Okay, so first you count up how many molecules or atoms there are for gases, for the reactants and the products. If there are no gases, then the side with more liquid or aqueous molecules or atoms has the highest entropy. Remember, aqueous means that it's dissolved in water. So if there are no gases, then you do the same thing with the liquid molecules or atoms, and you just count up the liquid molecules or atoms. If there are no gases or liquids, everything's a solid, then the side with more solid molecules or atoms has the highest entropy. Let's try an example. It sounds a little tricky and confusing, but it's really not. So example 13.6 on page 442 says, for each reaction below, determine the sign of delta S. So here's A. We have zinc, a solid, plus aqueous hydrochloric acid produces zinc chloride, aqueous, and hydrogen gas. So first we're going to look for the gas molecules. Not a gas, not a gas, not a gas. Here's a gas. So this would be one hydrogen molecule. H2 would look like this, right? So that's one hydrogen molecule. So there's one gas molecule on this side. There are no gas molecules on this side. So the products have higher entropy. So for the reactants, we are moving from, in this reaction, we're moving from low entropy to high entropy. In other words, the entropy S has increased. So is the sign for delta S going to be positive or negative? That is right. It would be positive. Okay, pretty simple. Let's try B. B is nitrogen gas plus 3 hydrogen gas molecules produces 2 NH3 or ammonia gas molecules. So this time we have all gases, so we have to add them up. On the reactant side, we have 1 N2 molecule and 3 H2 molecules for a total of 4 gas molecules on the left and 2 NH3 molecules on the right. So we have 4 on the left, 2 on the right. Which side is higher? Obviously the 4. So the reactants this time, the reactants have a higher entropy. So in this reaction, we're moving from high entropy to low entropy. So entropy has decreased. So the change in entropy is negative for B. All right, over here. Change in entropy equals negative. Now you might be wondering, you're thinking back to that inequality, aren't you? Delta S of the universe has to be greater than or equal to 0. Remember, we're not talking about the entire universe in this reaction. We're just talking about this reaction. So if delta S is negative for this reaction, then how it's affecting its surroundings must be greater than 0 to balance it out, because the entropy in the whole universe as a whole has to stay at 0 or above 0. Okay, and lastly, C. We have a solid. We have, oh, what was this one? This is another solid. Then we have aqueous, and a liquid. So we're going to concern ourselves with no gases. There's no gases, so we're just going to add up the liquids. And since the reactant side has all solids, the product side is all liquids, I know that the product side is going to have the higher entropy. So we're moving from low entropy to high entropy in C, which means that delta S would be positive. And that's how you determine the sign for delta S in a chemical reaction. One more thing. So this is my last video for Module 13. So for those of you in my class, you know that you are supposed to read to the end of the chapter, even without my notes, even without my video, and just do your best on the review questions and practice problems. And we will discuss in class tomorrow. Bye.